Thanks for joining us. Our session today is how to use Spark NLP to build a biomedical knowledge graph. We have two speakers, myself, Vishnu Vetrivel, I'm CTO of WiseKey.ai, and Alex Thomas, who's the principal data scientist at WiseKey.ai also. So WiseKey.ai, we help accelerate biomedical exploration research by building applications that combine the power of knowledge graphs, AI models, and of course a low-code, no-code platform. All right. So the main problems that, at least this talk is going to be focused on is there's three main problems we think that's happening in the biomedical space. One, we call it the biomedical big bang or big data bang, where there is a ton of new data being generated, whether it be research papers, scientific literature papers, whether it be like genomics data, or molecular data. There's a bunch of data that's actually being generated, which is great if you are a machine learning person or an AI person. The problem is, but it's not so great if you're a scientist who's actually trying to do work in the field. Because there's just too much data for one scientist or even a group of scientists to actually comprehend and make sense of it to do actual science. And the second problem, of course, is a lot of the insights are sort of hidden because behind papers, behind like human readable papers, because most of it is unstructured or unlabeled at best, right? And it's pretty expensive, which is the third problem, to actually generate labels in this domain. It's pretty expensive, given that, like, let's say, for example, in drug discovery domain, you actually have to, if you come up with a new compound or structure, you have to synthesize it, like run an assay, see the wet lab results. And by the time, you're talking weeks, right? And forget, that's just preclinical, but you get into clinical that, of course, we all know, like we're all experiencing COVID and how long clinical trials can take. So we're talking pretty expensive and pretty time-consuming efforts to actually generate labels. So this weird sort of paradox where in one side there's actually so much data being generated, but the other there's not enough to actually train models and do supervised learning on, which is where like things like deep learning and all these things really shine. So next slide. And so our solution, this is where we think NLP can really shine, right? So NLP, of course, there is possibility to take all of this sort of unstructured data and try to make sense of it, and combine that with the power of knowledge graphs. In some ways, the analogy, the metaphor is like the space metaphor. If you think about like, hey, there's all this sort of what I call dark data out there, where it's beyond the reach of science and comprehension. In some ways, we're sort of building a telescope. Like we're building the first space telescope to sort of point it at places we have no vision into, and we can find new insights, right? And so that telescope is like, what we think is a combination of both NLP and knowledge graphs. And, in this case, not NLP would be the lens and knowledge graph. I guess the application itself would be the telescope. But there's three main things that it has to do. It has to first, like, hey, visualize, point it so I can actually take pictures wherever I want, however further it is. And then I want to be able to explore and like, see what's happening, discover connections and concepts hidden, in that space. And of course, and then I want to learn. I want to experiment and I want to learn and I want to predict things. I want to, I want to predict that there's a planet out there that actually, resembles Earth, or, what have you. There's actually a new black hole that we found because of the way the planets move around a certain space, right? So those are the things that then become possible. Yeah, thanks. You can go to the next slide. And so that's sort of the overarching theme of like why we're so excited about NLP and knowledge graphs in the biomedical domain. And to hand it off to Alex at this point, he's going to take you into like, okay, so if that's what we want to do and that's why we want to do it, how are we actually going to build this telescope? How, we call it the Orpheus application or the pipeline. And so Alex is going to walk us through what that pipeline actually consists of, and what are the different details of actually constructing this application slash pipeline. Alex, take it away.
Thank you, Vishnu. Yeah, so I'm going to be walking through some details about how you'd actually build this. Here we have sort of a very high-end view of what we'll be doing. So we have our data sets that we take in that will be a mix of text data sets, unstructured data, and structured data. And what we want to do is we want to process the text and extract information from them and combine that with the structured data. And from there, we can do a large number of things with it, but we're going to be talking a lot about the knowledge graph. So We extract the text, we do topic modeling, and that's really useful for getting a high-level view of the corpus. If you want to understand what are frequent terms and groupings that occur within your text, topic modeling can be a great first step in exploring your text. Then from there, we extract entities. So that's going to be very important in different domains. So when people normally talk about finding, extracting entities or extracting concepts, it's referred to as sort of like this, like one single step. Actually, you're doing it for each of the different kinds of concepts or kinds of entities that you're interested in. Once we have those extracted entities, combined with the text data and the structure data, we can form a graph. So we can also bootstrap our own models for doing named entity recognition. So as we do extract entities, we can get better at extracting entities. We then build a knowledge graph from these extracted entities, and we can merge in new data sets. And as we merge in, we can actually learn more and more things from the knowledge graph. But enough talking about high-end stuff. Let's start getting into some details. So the first thing, let's talk about the data sets we're using in this version of Orpheus. So our text data is the COVID-19 data set. It's a data set of biomedical articles organized by the Semantic Scholar team in coordination with several government and private organizations and publishers. It contains articles, the actual articles in JSON files, and a metadata file. In the metadata file, it mentions over 200,000 different articles. Only about 90,000, at least at the time of this recording, are in the PDFs. So we restrict it to those. You can likely extract more by following URL links that are available in the metadata, but we're sticking with the 90,000 immediately available. So once we have this text data, we want some structured data to use as well. So we have a manually created list or curated list of disease names. So we're going to use this as a dictionary-based for dictionary-based entity extraction. Then we also have data from Kemble and Uniprot. So these are sort of like very major databases of chemicals and proteins, respectively. We have subsets that we've gathered that are more germane to stuff that occurs in biomedical literature. So the infectious disease data set was took about 10 hours to curate. The other ones sort of came with all their data, so there wasn't much manual creation required. So let's look at the COVID-19 data set. So there's about 94,000 documents that we have, at least as of this recording, and they have an average character length of about 26,000. So we can see that there's a large distribution of different journals. So there, if I recall correctly, there's about, there's 20,000 journals and PubMed Central. The licenses that they have also are listed in the metadata set. So here we have, I guess, no Creative Commons and various other abbreviations for the licenses there. So there's a wide variety of different sources and different licenses available for this. And so now that we have this data set, it's not enough just to look at what texts are. We need to actually process this. So we're using Spark NLP. So Spark NLP is a library that I worked on, and actually I recently wrote a book on it. So it's built on top of Spark MLlib. It lets you build your own pipelines. It comes with many great pre-built pipelines and pre-trained models. I created my own pipeline, but that's because I had very specific needs that I wanted for this pipeline. But I did use some of the pre-trained models. So let's actually look at what my pipeline looks like. So the first step, which is very common, is to do sentence tokenization. So what that means is you're splitting your document into a list of sentences. Then from there, I tokenize. Now, the reason why we see two different tokenizing steps is that at this point, I have two outputs for my text. One of the outputs is going to be used in topic modeling, and one is going to be used in the entity extraction. I don't want to do as much processing on the entity extraction as I do on the topic modeling. So the reduced one here, the reduced pipeline here, this is the named entity extraction view of the data. This is how I'm going to be finding the entities. This one here has much more aggressive normalization. So the tokenizing is grouping together common Engrams. I'll go over how we got those in a moment. A little bit more aggressive normalization, getting rid of overly short words, removing stop words, and lemmatizing, so reducing words to their dictionary entry. And then I save both these views of the data. So I save the normalized tokens from this reduced one, and I save the lemmas for the topic modeling. So when we want to find the Engrams, which is going to be important in the topic modeling, because a lot of these phrases that may be important may not be single word phrases. So what we need to do is we need to see what are the frequent sequence of tokens that will be these common phrases. So this is an example of a manual process to do it. There are other automatic ways you can do it around different heuristics or even around model-based approaches. A lot of the heuristics tend to be error-prone, especially if your data has many formulaic phrases. For example, in this data set, many of the documents have copyright and usage statements on every page. And so if you are extracting common phrases, it's going to find those phrases. And what that will do to the topic modeling is your topic model will think those documents are all related because they have the same sequence of tokens. And you'll think like, oh, these are related, when actually the only thing that relates is they used similar copyright headers. So the manual process, we generate Engrams. So that's a sequence of tokens of length n. Here we're looking at length 2, 3, and 4. Usually after 5, it starts getting very sparse. We identify stop phrases, which is these formulaic copyright statements or links. And then we identify phrases we want to keep, and we just add them back into the tokenizer and rerun the NLP pipeline. And then once you're satisfied with the output, you can move on with the processing. So let's look at some of these distributions of Engrams. So here we see the log mean of the TF-IDF. So just in case some of you are not familiar with TF-IDF, it's a formula for weighting words and how relevant they are to a document. So the idea that TF is the term frequency, so that's how often it occurs in the document, and IDF is the inverse document frequency. So it's the inverse of how many documents it appears in. With the idea that if a word appears in many, many documents, you want that to be weakened, you want it to have a lower weight, but if it occurs many, many times in this particular document, then you want to boost that weight. So looking at the mean TF-IDF sort of gives you an idea of how this these terms are distributed across the corpus. So here, if we look at the mean TF-IDF of unigrams, we see that it's sort of a shallow decline. And this is the log, so if you saw it without the log, they would all sort of look the same. With bigrams, it gets a little bit sharper, trigrams sharper still, and 4 grams, most of the 4 grams occur very rarely, both across the corpus and within a document. So once you've added the Engrams in your manual process that you want, you can go on to do the topic modeling. So topic modeling is based off of this idea that you shall know a word by the company it keeps. So this comes from the idea that semantics are related across words. So if I don't know what a word means, but I know the words around it, then that gives me a sense of the meaning or of the domain, so to speak, of that unknown word. So this is the idea behind latent Dirichlet allocation. It's also the idea behind word2vec and BERT. It's a field called distributed semantics. So we're going to be using latent Dirichlet allocation here, which is a clustering technique built for language data. And we're using a program called PyLDA-Viz to do the visualization. So this is just a frozen example. The PyLDA-Viz library actually has an interactive widget here that it produces if you're running in a notebook. It's very useful for getting a good read on your topic model. So now that we have the topic model, we can get into the entity extraction. So there's two basic approaches to entity extraction. There are dictionary-based approaches and model-based approaches. So the dictionary-based approach is generally done with some sort of a search try, and in this case, we're using the AutoCorsic algorithm, which is an algorithm that lets you efficiently search for many different words. It requires a dictionary or a word list for you to search for, but it doesn't require any training data, as this is purely based off the dictionary. A model, generally in recent times, they're deep learning models, though conditional random fields were prominent until maybe 5 years ago, and they still actually do perform well. All the state of the art, all the top of the different benchmarks are deep learning, but conditional random fields aren't too far off in terms of their metrics in this field. So the AutoCorsic algorithm it allows us to do the search efficiently. So one of the problems of this search is that you don't want to search a piece of text and then have to search that piece of text many times for each one of your words. Really what you want to do is do a single scan through all your text and know when you've run across a word. So the AutoCorsic algorithm essentially does that. So this is, on the right-hand side, is a visualization of a very simple word try. So the idea is that you're coming across the word, let's say acute or common. So let's say I come across acute. Well, if I go to bacterial and then rhinusitis, I'll find the entry for the sinusitis disease. If I go to common, oh, this should be cold here. If I go to common, then cold, I should get common cold. And the cool thing about the AutoCorsic is that there are extra links in this try that keep you from having to backtrack over your text. The downsides to the dictionary-based approach is that you could only find the entities in your alias list, and it does not use context. So if you have a protein named April, as there is one, anytime someone mentions the month April, the AutoCorsic algorithm obviously won't be able to tell the difference. It's just, it has that token. And so it will say, oh, we found the April protein all over these documents, when you likely have not. The model-based approach predicts which tokens are part of a reference to an entity. So if we see on the right-hand side here, this is something called the bio format. So the idea is that each one of these tokens that is not in an entity reference, it's not in a phrase that's referring to an entity, is marked as O, so outside of an entity. And then the first one is marked as B, so this is the beginning of a disease, and then all the rest would be marked as inside a disease. So here we have influenza virus is a reference to a disease, and so it would be marked as such. Pros to it are, it identifies based on context, so it's the opposite from the dictionary-based approach. You can find things that you didn't know about because it's looking at the pattern of words around it to say, oh, this is a disease, and it can be tuned to different data sets. So you can have a general NER model, and you can actually try and tune it to your specific data set. The downside is it requires training data, and if you're doing deep learning, it requires a lot of training data, and this training data can be difficult because you can farm out generic text to get labeled, but in domain-specific data like this, you actually might miss a lot of instances if you if you give it out for general people to do it. They might miss references to diseases or chemicals or proteins. So once you have the dictionary-based model, though, you can actually use it to bootstrap a entity extraction model. So the way it would work is that you would run your dictionary-based approach and output the data in a bio format, just as we showed before. One important thing is that your tokenization must be consistent. So this is now a common problem with a lot of pre-baked deep learning-based named entity resolution models, because they often come packed with the specific tokenization that's required. The dictionary approach you're bootstrapping from and the model you're building, you should be fine. You can, if you have a small set of data, you should probably go with a CRF. Difficulty is it has fewer open source implementations, but they are out there. There's definitely, it's available in Mallet. There's actually several C-based libraries that you'd probably use as a command line tool. If you're doing deep learning, you can get really good scores, so you can actually train the basic model on the output from the dictionary, and then as you acquire more data, whether it's from human labeling or if you find data sets relevant to that entity type, you can improve your model. Of course, the downside is it requires lots of data, and it's slow to run without a GPU. And depending on the complexity of your deep learning model, it can actually be slow to even evaluate without a GPU. One of the complications with embedding models like BERT is that it is running a neural network in order to produce the embedding for the words. And that means that if you don't have a GPU, you can get something that runs really slowly. So that's something to keep in mind when you're evaluating how you want to approach your named entity extraction. So now that we have our entities, we can talk about graph building. So again, we want to extract these relationships between the entities, and we can look at a heuristic approach versus a model. The heuristic approach, it has a lot of benefits here. The data sets for models for extracting relationships are pretty rare, at least compared to NER models, and creating labels requires experts. If you give a sort of a lay person these biomedical texts and ask them how a given protein and a given compound are related, they're not going to be able to give meaningful answers. Now, you could try and do heuristics based on the text. So, maybe if they're referred to in the same sentence, you can establish a certain relationship based off the words in the sentence. The problem is that certain styles of language can be excessively verbose, and that means that the entities that are related can be spread across multiple sentences, and there can be a lot of artificial extra words put in there to pad word count or to sound or to sound more academic. So here's some pseudo Python about how it is. So let's say we have our document entity matrix. So we have that here. That's X. That's the number of, so Xij is the number of times entity J occurs in document I. Well, we can define a binary one, and then we can get a co-occurrence one from that one. And so that's pretty simple linear algebra operation, and that will get us the number of Cij will be the number of documents with entities I and J, and Cii will be the number of docs with entity I. So what's cool about that is that from there we can look at the things that could possibly be edges. So we just select our edges to wherever C is greater than 0, and just because in this case it will be symmetric, the matrix. We just select a certain part, up or down from the diagonal. And so now that so now that we have that, we can also calculate the document frequency of these entities. So here, if we just sum across our binary one, we get the number of documents it occurs in. And now we can calculate TF and IDF for our entities. Relatively straightforward. And then we have a TF-IDF matrix of our document entity occurrences. So what's cool about that is that now that we have a list of our edges, we can actually go through those edges and use either Jacquard or a weighted Jacquard based off TF-IDF and use that as a weight for our edges. So now we have our full model here. So we can pre-calculate the data necessary for the LDA visualization. We can load the articles and entities and topics into a search index, and that will let us have a nice decorated search engine. And then we can load the entities and edges into a graph like OrientDB or Amazon Neptune. So here, we see the corpus, NLP pipeline, the two different entity extraction approaches, LDA, and then we do our graph building, and everything has come together, and we can put our app up now. So let's go and look at the Orpheus application. So here we see the landing page. Now this is going to look a little bit different than the one generated in the slides because it's generated from a different set of data. These are topics and these are our terms. So it looks like we probably missed a couple stop words in this one. Here we have some recent papers and we have some top entities here. And so that lets you look at sort of the stuff that's prominent in this data set. Let's go ahead and go and search for something. So if we go here to topic 0, we see the distribution of words. As you can see, there's not a lot of difference in this topic. That probably means LDA needs more iterations. But I can click here. Now we can go and search. And here we have a search for cytokine in our search engine. So we see a bunch of documents that reference cytokine. We see a mathematical model of cytokine dynamics during a cytokine storm. Let's go real quick here to, let's see. Up here. So we can click here to through the cytokine storm for COVID-19. We can click through here, and now we can see our graph view. Click here, and we can actually extend the graph. And now we have the nodes connected to COVID-19 and the nodes connected to ACE2. And here we have remdesivir, which is a drug that got some attention. And we can see, well, why is ACE2 connected to remdesivir? And here are the articles that are stored with it. So we have all this data now that we've organized from structured and unstructured data that can talk to each other. So yeah, we have the abstracts available here. So that's it as far as for the technical details. So I'm going to hand it back to you, Vishnu.
All right. Thanks, Alex. Yeah, so just wrapping up in conclusion. So we saw like, hey, how can we take all this dark data really, and then using NLP sort of, being able to extract not just the entities and the concepts, but also then being able to, the relationships that are sort of inherent in that data and sort of build out this knowledge graph pipeline, which of course we didn't even get to, but like there'll be a whole other talk where we can talk about like okay, now we have this knowledge graph, what are the downstream use cases, anywhere from link prediction to like adverse event prediction to like generative modeling in the drug discovery case. There's so many use cases that now open up because we have this biomedical knowledge graph actually built out. Anyway, I wanted to leave you with an image of the, one of the famous images that Hubble Space Telescope actually took. So I think it's the Pillars of Creation from the Eagle Nebula. But the point of it is like going back to the metaphor, there is a lot of data, and we believe NLP and knowledge graphs are going to help us see that in a much more clearer way. And it's going to be an amazing sort of vision once we actually are able to do that in this space. So thanks a lot. I think that's our time. And now we'll take questions.